Okay, so let's begin by quickly reviewing where we left off in the last lecture. So remember, last week we ended by spending the second lecture for the week discussing in detail this notion of a Fourier sine series. And so the general problem we were considering was, suppose you're given a function, say phi of x, right? And so the question is, when is it possible to write phi as a sum of some combination of sine waves that are oscillating at different frequencies, some discrete collection of frequencies. And in particular, we had the formula sum over n is going from 1 to infinity, sine of n times pi over L times x, where L is like the length of your interval, right? So x is between 0 and L. And so the question was, which arose when we were looking at certain boundary value problems, was, well, is it possible to write an arbitrary function phi of x in this way? We still don't know the answer to that question. The other question, which we did address, was, well, suppose you know that your function phi of x is given to you by this formula. Again, from the motivation from studying the boundary value problem for the wave and diffusion equations, we expect that we need phi to be of this form in order to actually write down a solution to the partial differential equation. Then the question is, well, how do you calculate these coefficients? And so we answered that question by developing a notion of orthogonality for functions with certain boundary conditions. And then we use this concept of orthogonality, or perpendicular functions being somehow perpendicular, to derive the formula for an. And so for the first part of this lecture, I want to do the same thing, but now for series involving cosines. And so these turn out to be equally important. And then after we discuss this theory in a little bit of detail, we're going to combine everything to look at what's called a Fourier series, which combines like the sine and the cosine terms. And so at the end of the last lecture, we already began discussing the cosine analog. And so the motivation is the following. Again, these problems are all motivated by problems from studying partial differential equations, and in particular boundary value problems. And so in this case, the boundary value problem to look at is the diffusion equation. So we have ut minus k uxx is equal to 0. Again, we're on a bounded region between 0 and L. And while time is unbounded, time can just be bigger than 0. But notice we're changing the boundary conditions. Instead of, remember for the sine problem, we had u of 0 t is equal to u of lt is equal to 0 for all t. Right, so this is like the standard 0 boundary condition. So for the Neumann boundary condition, instead you require that the derivatives are 0. Sorry, this should say equal to 0. Right, so we're requiring that the first derivative with respect to x is equal to 0 at both x equals 0 and x equals L for all time t. Right. Okay, and you can solve this problem using separation of variables, as we've seen for several examples previously. So this problem is on your homework which is due at the end of this week. It's on homework 6. You just use it'll be very similar to the other separation of variables examples we've looked at, and in particular the calculation you did in detail on homework 3. And so in this case, once you apply the method, you see that you expect the general solution looks very similar to what we saw for the 0 boundary value problem without the Neumann conditions, but instead you have cosine terms instead of sine terms arising here. And also there's some coefficient corresponding to n equals 0. Right, and so in particular, this means that, right, if I write down, well, let's look at u of actually, no, never mind. Right. So I mean, the main thing I just wanted to point out is that there could be a coefficient corresponding to n equals 0, which was not the case for the sine term, mainly just because, well, when x is equal to 0, we expect the function to be 0 for the boundary value problem associated to sine. Okay, and so what we're going to do is go through something similar to what we did with the sine series and talk about, well, for one, what is there a formula for these coefficients, right? So assuming that I know my function can be written in this way, how do I find the coefficients, right? And so this is going to have a very similar answer to what we looked at for the case of sine series. So one thing to point out is, well, let's suppose that I have an initial condition, which you typically will need in order to say anything more meaningful about the solution, right? So suppose at time 0, my function is equal to phi of x, and I plug in this formula. Well, if I plug in t equals 0 to this formula, I get the following. Well, I need phi of x is equal to 1/2 a0. Well, the first term doesn't depend on t, so that just stays. And then, well, if I plug in t equals 0 to this infinite sum, the only thing that depends on t is the exponential term. And when I plug in t equals 0, I have e to the power 0, so I get 1 for that. And so I just end up with sum from n equals 1 to infinity of an times cosine of n pi over lx. And so this is what's called a cosine Fourier series. Or Fourier cosine series if you switch the order. I mean, it'll be written in right, you'll see people write this in different orders. Right, and so what we're gonna talk about is how to find a formula for an. The formula is going to be very similar to what we saw for the sine case, and in fact, it's going to use the same idea. The first thing I wanted to talk about, though, before we do that is, well, remember before we derive the formula for the coefficient in the case of the sine series, we talked about some connections with linear algebra, and in particular, we talked about this notion of an eigenfunction, which is kind of like an eigenvector for the differential operator. And so I just want to talk about the analog here. And so you'll remember that when we mentioned this, I pointed out that it's very important to keep track of what the boundary conditions and the domain of the operator are, because this can affect what the eigenfunctions are. And we're going to see why now with this example for the cosine case. Okay, so I just want to talk about eigenfunction interpretation. And so we're going to consider the differential operator, which will be the same as what we looked at in the last example. So I'll call A is minus second derivative with respect to x, right? So this means that it's a differential operator, which means I apply it to functions to get a new function. And the rule is, well, you take the second derivative with respect to x, and that's the output of the operator. And so here's going to be, so this is the same operator we looked at in the previous lecture. The change is going to be the domain, right? So we're no longer going to be considering this operator with 0 boundary conditions as we did for the case of sine series. We're going to be considering it with Neumann boundary conditions, which is more reasonable for the Neumann PDE problem, right? Right. So we're going to be considering domain of functions. Let's say on 0, x is between 0 and L, with Neumann boundary conditions. Right, and so the functions will satisfy, well, if I take the x derivative at 0, this should be equal to 0. And if I take the x derivative at L, this should also be equal to 0, right? But, right, since we're not assuming the boundary conditions from before, we could have phi of 0 not equal 0, or phi of L not equal 0, right? Right, and so again, the key new difference with this example is the domain has changed, right? Because now we're considering, instead of imposing the previous boundary conditions, we're now imposing the new Neumann boundary conditions. And so this is going to end up affecting what the admissible eigenfunctions are, right? And so, well, for example, recall So if right, so for this operator A, we looked at these functions sine of n pi over Lx, which we called Vn of x. It's certainly true that if I apply A to these functions, we saw that, well, you get something like the eigenvalue formula. So you get n pi over L squared times Vn of x, right? And so this is like the eigenfunction formula, which should remind you of the eigenvalue formula from linear algebra, which is, right, so you apply a matrix A to a vector and you get some lambda times the vector. Right, so these were eigenfunctions, but they were eigenfunctions for the problem with the zero boundary condition, not the Neumann condition. Right. And so in particular, well, we can check just by differentiating that these functions Vn of x, or the sine of n pi over L times x, these functions do not satisfy the Neumann boundary conditions. So for the problem we're considering now, they're not in the domain of the operator, right? So notice that, well, if I take derivative with respect to x of Vn of x, right, this is derivative with respect to x of sine of n pi over L x. Derivative of sine is cosine, and then I have to use the chain rule. So I get n pi over L times cosine of n pi over L at x. And so if I look at the derivative with respect to x of Vn at 0, this is just n pi over L times cosine of 0, which is not 0, right? This is n pi over L, which is not 0, right? Because n is bigger than or equal to 1. And so these are not in the domain, right? So let me call this domain D. For the Neumann problem, right? So the point, and so this is just to further elaborate on the point I made in the last lecture. The point is that the domain is very important for the problem that you're interested in, right? We didn't change the operator. We're still looking at the same operator from the last example, but we're imposing different boundary conditions. And so it's going to turn out that the new boundary conditions require possibly different eigenfunctions, right? So the eigenfunctions we had from last time, it's still true that if I apply the operator, I get a constant multiple times the function, but they don't have the same boundary conditions, right? And so in particular, if I want to use these eigenfunctions to find a solution to this partial differential equation with the Neumann boundary conditions, the sine functions are not going to work, because if I take any combination of those, they're not going to satisfy the Neumann condition. They satisfy a different boundary condition, right? So the summary is that the boundary condition you're working with for your boundary value problem will impose restrictions on what type of eigenfunctions you'll work with, which relates to like what type of infinite series you'll be getting as your solution formula, right? And so in particular, well, you can hopefully maybe kind of guess that just from like similarity, we would expect that the eigenfunctions for the Neumann problem are not sine of n pi over L, but instead cosine of n pi over L. And so this is going to turn out to be the case. So I'm not going to elaborate too much on it. We'll just kind of check that they work. Right. So let me just call this. I guess I can call this a theorem. Right. So I'll break it up into two parts. So the first part is the functions. Let me call them, instead of v, since I used v before, let me call them w n of x, which are given by cosine of n pi over L times x. So these are eigenfunctions for the operator A on the domain D with Neumann boundary Neumann boundary conditions. Right. So that's the first part of the theorem, and then the second part is the orthogonality, the analog of the orthogonality result, which is if I look at the integral from 0 to L of cosine of, say, n pi over L times x times cosine. So I look at the product of two of these eigenfunctions, and I integrate them on the domain, right? So, and well, I have to scale. So let's say I scale by 2 over L. Then this is equal to 1 in the case where m and n are equal, and it's equal to 0 otherwise, right? So this is like the same formula we had for the sine eigenfunctions and the other boundary value problem. So with the orthogonality notion is preserved. Right, and one thing, right? So let's prove this theorem. One thing I want to just remark. Well, what happens? We're allowing n equals 0 here, right? So n can equal 0, 1, 2, 3, up to infinity. So in the n equals 0 case, well, when I plug in n equals 0, I get cosine of 0, which is 1. So the function 1 is an eigenfunction. Right. That's part of the claim, which was not the case for the other boundary value problem. We looked at it in the last lecture. Right. Okay, let's just do a quick proof of this result. So let's first consider part 1. The first thing to check, which is easy, is that, well, if I take minus the second derivative with respect to x of cosine n pi over L times x, this is equal to, well, derivative of cosine is negative sine, and then the negative signs will cancel, so I get d dx, and then I have to use the chain rule, so n pi over L sine of n pi over Lx, and then I take one more derivative, and I end up with n pi over L squared cosine n pi over Lx, right? And so, right, so this says that if I apply A to Wn of x, I get n pi over L squared Wn over x. And so this quantity here, which is sometimes denoted lambda n, is the eigenvalue, right? And so this shows that these functions solve this eigenvalue equation, right? So that's the first part. But the second thing that we want to check is not just that they solve the eigenvalue equation, but that they have the correct boundary conditions, right? We need the Neumann boundary conditions. Otherwise, these functions are not in the domain that we specified, right? Remember, we specified this particular domain D. Okay, and so let's just quickly check, right? So let's say I take derivative with respect to x of cosine of n pi over Lx. This is going to be n pi over L negative sine of n pi over Lx, right? Well, when x is equal to 0, this is, well, sine of 0, I get negative n pi over L sine of 0. Sine of 0 is 0, right? On the other hand, so that's the first condition, right? We want 0 derivative when x is equal to 0. We also want 0 derivative when x is equal to L. Well, when x is equal to L, we get negative n pi over L, and then I have sine of n pi over L times L, so the L's will cancel and I get sine of n pi. Sine of n pi is always 0, right? The sine of any integer multiple of pi is 0, so that's also 0, right? And so, right, so these are in the domain. right? And so when you're given like a differential operator with a domain that's specified to you with certain boundary conditions, if you want to check that some function is an eigenfunction, you have to check two things, right? You have to check that it solves this equation where if I apply the operator to the function, I get a scalar multiple of the function, and then the scalar multiple is the eigenvalue. But you also need to check that the functions under consideration are in your domain, right? So that's very important. Right, so that's the proof of part one of the theorem. And then the second part is this notion of orthogonality. So this is just a trig integral calculation, which is very similar to what we did in the case of sines. So you're going to use the double angle formula to rewrite the integral, and basically just the same way as we did with the sine case, but you just interchange the role of sines and cosines. So I'm going to omit that from this lecture, but if you want to see this in detail, I can do it during one of the Zoom meetings or in office hours. So for part two, it's a calculation that's very similar to what we saw in the last lecture. So I'm not gonna do that here. Okay, and then finally, well, now let's suppose I have my function phi of x, which is given by 1/2 a0 plus some n equals 1 to infinity of right, so I have my function given by this cosine series. And so what I'm going to do is, well, let's ignore the 1/2. Let's absorb the 1/2 into the definition of a0, right? a0 is just some constant, so 1/2 times a0 is also a constant. So I'm just going to relabel things so that I don't have to worry about the 1/2. So what we have here is this is exactly an eigenfunction decomposition in the sense we described last time. Right, so I'm writing phi as a sum from now n equals 0 to infinity of an times wn of x, where these are the eigenfunctions for the operator a, which was minus second derivative with respect to x, right? And so, well, remember we also have, they're not just eigenfunctions, we have this orthogonality property, which we also had for sines, right? So these are orthogonal eigenfunctions for this operator on the Neumann boundary condition domain. Great. And so this is exactly the analog of what we saw last time. If you view the decomposition from a slightly more abstract level and think of it not as a sine series or a cosine series, but instead as an eigenfunction series where the eigenfunctions are orthogonal, it's the same formula that we saw last time, right? It's just that for these particular boundary conditions, you change the eigenfunction, but otherwise it's the same formula for what phi needs to be in order to solve the equation, right? It's the same idea. Okay, and so the final question to address is, well, let's suppose we have an infinite sum like this, and let's suppose it converges and the function phi is equal to the sum. So then what are the coefficients an, right? Well, since we have this decomposition and since the eigenfunctions have some notion of being perpendicular, you would expect the formula to be very similar to what we saw last time. And so this is the case, right? So if I look at this particular an, it's going to be given by, well, you have to rescale to take into account the length of the interval. So we have to have this 2 over L factor, but otherwise it's going to be 2 over L times integral from 0 to L And what did we do last time? We multiplied the function phi by the eigenfunction. And so in this case, this is phi of x times cosine of n pi over L times x dx. Right? So this is the case if phi of x has this form. Right, and so this is for n, sorry, this is for n bigger than or equal to 1. And well, what is the n equals 0? Right, sorry, I just confused myself with the deleting the 1/2 and then right. So if n equals 0, it's going to be 1 over L times integral from 0 to L of phi of x dx. Right. Right, and so this is going to be proved in exactly the same way as we saw last time. So the proof idea is just, well, let's suppose phi of x, I can write phi as a sum from n equals 0 to infinity of an times these eigenfunctions. And so if I look at the integral of phi of x times some eigenfunction, say wm, where wm is again cosine of m pi over L times x, right? So this should be equal to the sum from n equals 0 to infinity of the integral, again, this is from 0 to L, of phi of x times, or sorry, of wn of x times wm of x dx. And so this is 0 unless n is equal to m, right? And so therefore, if I look at the integral from 0 to L of phi of x times wm of x dx, this is equal to, well, the only non-zero term that appears in the infinite sum is when n is equal to m, right? So it's equal to the integral from 0 to L of wn of x, wm, n and m are the same thing, so let me clarify, wm of x times itself, right? Since the other terms vanish, well, then we saw previously, we know what this is equal to, so this is equal to L over 2, right? So this is now equal to L over 2. This is just a trig calculation, which you have to do, or if you integrate, so this is like cosine of m pi over L x squared. And so you have to use some trig identity. You can evaluate this. Right, sorry. When I wrote this sum up here, there should have been an an here, right? And so then the only coefficient that remains is the coefficient for am, right? And so therefore, this tells me that am is 2 over L times integral from 0 to L of phi of x times wm of x, right? Right, and so this is in the case where, right, so if I integrate wm squared, this is when m is not equal 0. Let's do the m equals 0 case independently, and this should clarify the confusion from before, so I apologize for that. Well, in the m equals 0 case, I'm looking at integral from 0 to L of phi of x times w0 of x dx, which is just 1. And so this ends up being the sum from n equals 0 to infinity of an times integral from 0 to L of just w0 of x times w n of x. And so just as before, this is 0 unless n equals 0. Again, it's a similar calculation. And so you end up with, well, there's only the term corresponding to a0. I have a0 times integral from 0 to L of 1 dx. So this is a0 times L, right? And so this tells you that a0 is 1 over L times integral from 0 to L of phi of x. w0 is 1, so it's just phi of x dx, right? Right, so this is for m not equal 0. Right? And that's what I wrote up here, right? Okay. Sorry, I just want to double check the formula up here. Right. So you have to clarify in this theorem from earlier. So this is in the case when m is not equal 0. If m equals 0, of course, it's still true that if I have cosine of n pi over L times x times 1, and I integrate that, I get 0. The only difference is with if I look at the case where I'm integrating cosine of 0 times cosine of 0 from 0 to L, that's not going to give me L over 2. It's just going to give me L. Right? That's the one minor addition that. Okay. All right, so that's about it for what I wanted to say related to the theory of cosine Fourier series. So we still haven't really done many calculations, which we'll do some of at the end of this lecture and at the beginning of the next lecture. What I want to do now, though, is try to put together the two lines of investigation that we've been looking at in terms of Fourier cosine series and Fourier sine series. And so it turns out for more general problems in math, and also in partial differential equations, but in math more generally, you're not just interested in either a cosine Fourier series or a sine Fourier series, because remember, these respective objects are deeply connected to two specific boundary value problems. But in general, you may have different boundary conditions, or you may be interested in another problem where you have to decompose your functions in this way. And so in this case, it helps to combine the two notions. So we're going to talk about full Fourier series. And so this is really just, I mean, it's exactly what it says, what it sounds like. So we're going to combine the sine and cosine Fourier series into one object, right? And so in this case, this is actually, it's a bit of a jump. It'll become clear why we're doing this as our study of Fourier series progresses. So we're going to assume, we're going to change the domain a little bit for the functions. So we're going to assume the domain is between, instead of x bigger than 0, x is bigger than minus L and less than positive L, unlike from before, right? So this is going to help with symmetry, which makes some calculations easier. So previously, because we were motivated by the boundary value problem, we considered x between 0 and L. right? And so this is something that the book does, so I need to match up with it. So maybe this could be potentially confusing. In this book, when we're talking about full Fourier series, which I'm about to define, the domain is always between minus L and L. And in particular, when we compute the Fourier coefficients, you're going to have to be integrating over this domain between minus L and L. On the other hand, for sine and cosine series, as we just looked at, the domain is between 0 and L. So all the integrals are over 0 to L. It's kind of an annoying technicality, which you're going to have to keep track of for a little bit. Right. Okay, and so let's suppose that we're given a function phi of x, which is defined on, say, open interval between minus L and positive L. Right, and so the definition, we say that phi of x has a Fourier series on this interval if the following holds. So if I can write phi of x as a sum of terms like we considered previously. So if I can write phi of x as a sub 0 plus now a sum from n equals 1 to infinity of an of the cosine functions. So I have the cosine terms from before, plus some other constant coefficient. So let's say bn instead, times sine of n pi over Lx. Right. And so now it's not just a cosine series or just a sine series, but we're just combining the terms for each n. Right. So I have the n equals 0 term over here, and then I have the higher n terms. Right. And so these numbers are called the Fourier coefficients. Right. And so there's going to be some collection of Fourier coefficients which correspond to the cosine terms and some collection which correspond to the sine terms. And so we're going to have formulas which are very similar to what we saw previously that will allow you to calculate what these coefficients have to be. So for about a week, we're going to have to keep distinguishing between the cosine Fourier coefficients and the sine Fourier coefficients, and doing separate calculations to determine what respectively they're equal to. We're going to see next week that there's actually a way to combine these together into a much easier fashion using complex numbers or imaginary numbers. And so we're going to have a lecture either beginning next time or at the beginning of next week, where we introduce complex numbers in more detail and talk about how to simplify a lot of the calculations we're doing here. So if a lot of these calculations seem to you to be maybe like overly long or redundant or something like that, we're going to simplify them soon. But in order to motivate what we're going to do, it helps to first look at this particular case. Right, and so just as with the cosine series and the sine series, for the full Fourier series, we still have certain orthogonality properties. So I'll write this as a theorem. So we have the following additional orthogonality properties. Right, and so if I look at the integral from minus L to L, and let's say I take the cosine term, so cosine n pi over Lx. Well, what's the new addition here? We have to consider what happens if you not just multiply a cosine term times another cosine term, or a sine term times another sine term. We have to see what happens when you multiply some cosine eigenfunction times some sine eigenfunction, right? And so it turns out that if I calculate this integral from negative L to L, this is always equal to 0 for all n and m. Right, so this is the new addition. And so similarly, we still have the previous formulas. So if I look at integral from negative L to L of cosine n pi over L times x times cosine m pi over L x dx, this is equal to 0 if n doesn't equal m, right? The only difference being is we've replaced, right? So this is negative L, not 0, right? But otherwise, it's the same thing, and then you can do the same calculation to check, right? And so again, since we've increased the length of the interval, we expect that in the case when n is equal to m, that the value of the integral should increase. And since we've doubled the length of the interval, it turns out that it actually will double, basically because of the symmetry related to trig functions. So this ends up being L rather than L over 2, right? But otherwise, it's the same thing. And so this is also true for if I have sine instead of cosine. Right. Right, and so to prove this last formula, it's the same calculations we saw for the case of sine Fourier series or for the case of cosine Fourier series. And then the only new addition is showing that if you have cosine of n pi over L times x times sine of m pi over L times x, that this is always equal to 0, even if n and m are the same number. Right? So like the cosine terms and the sine terms are perpendicular or orthogonal to each other. Right, and so you can evaluate this new integral using some more trig examples. So I think I'm going to omit the calculus computation to show that this is equal to 0. This may seem like a bit of a cop out, like it's not immediately obvious how to show that this is 0. But if you work at it for a little bit, you can probably do it. However, the main reason I'm skipping it is because in a few lectures we're going to see a much easier way of proving things like this using complex numbers, as I said before. And in that case, I'll prove everything directly. I'll do all the calculations for you. So just to save some time, and since we're going to have a better way to do this in a few lectures, I'm gonna skip this calculation. But it's not too hard to check. Right, and then finally we have a theorem which will look very familiar about what are these coefficients actually equal to, right? So what is a formula for an and what is a formula for bn? So the formula is the following. So if phi has a Fourier series in the sense above, you must have an is equal to 1 over L times integral from minus L to L of phi of x times cosine of n pi over Lx dx, where n equals 0, 1, 2, etc. And bn has to equal 1 over L times integral from minus L to L of phi of x times the sine term, right? Sine of n pi over Lx dx. Right, and so these are exactly the formulas we had from the respective cases of Fourier and sine series, and so they reappear here when you look at the full series combining these two things. Yeah, so I just realized that this idea of absorbing the 1/2 from before turned out to not be very helpful of a simplification, because all these formulas in the book take into account this normalization. So if I change all these formulas, I'm gonna confuse everyone. So I'm gonna retroactively go back and pretend that didn't happen. And in that case, if you normalize the coefficient a0 in this way, then these formulas are valid also for n equals 0. I mean, it's in any case you can always check just by calculating in the integral. It's not a big thing. It's not as big of an issue as I'm making it out to be, but I don't want to confuse people. So for us, let's continue with the book's notation and have 1/2 a0 for the first term. Right, and so how do you find these formulas? Well, these formulas are derived in exactly the same way as for the cosine and sine series because we have the crucial orthogonality relations, right? So let's say, for example, I wanted to find, let's say I wanted to find an, right? Well, let's integrate my function from negative L to L, phi of x, against this cosine term. So against cosine of n pi over L times x dx. Well, let me expand phi into the Fourier series. So this is going to be sum from n equals 0, or let's say sum from n equals 1 to infinity, integral from minus L to L of an times cosine of right, so let's sum from m, not sum from n. Right, so expanding phi into as a Fourier series, this is equal to am times cosine of m pi over Lx. So the term corresponding to this value plus bm times sine of m pi over Lx, all multiplied by this cosine term dx. And then we also have to have the term corresponding to n equals 0. So plus integral from minus L to L, 1/2 a0 times cosine of n pi over Lx dx. Right. So this looks like kind of like a complicated calculation, but let's distribute everything. So I have the first term corresponding to the a0 piece. Right. And then I'm left with, well, okay, well, I have this sum m equals 1 to infinity. This integral is going to break up into two pieces. So I have integral from minus L to L, am times cosine of m pi over Lx times, well, let's distribute. So cosine of n pi over Lx dx. And then I have the other piece corresponding to the bm terms or the sine terms. So I have sum from m equals 1 to infinity, integral from minus L to L, bm times bm sine of m pi over L x times cosine of m pi over L, sorry, n pi over Lx dx, right? So that was kind of long-winded, but all I really did was just plug in, right? So we're assuming phi has this Fourier series, so let's just plug it into this integral for phi, replace phi by that series, and break everything up, and that's all I did here. Right? I didn't do any other math. Okay, well, we have these orthogonality properties, and so what these orthogonality properties will imply is that every single term in the expression I just wrote out is going to be 0 except for one term, right? Right, so every term is 0 except where m is equal to n, right? And so this is the orthogonality. And so let's just suppose, for example, that n is not 0. if it's equal to 0, you have to handle that term separately. But let's suppose it wasn't 0, just to simplify matters a little bit. Well, then we end up with integral of phi of x times cosine of n pi over Lx dx. Well, it's only equal to the terms when n is equal to n, so I get integral minus L to L of an times cosine n pi over L x squared dx. And then I have the cosine and sine term, so minus plus the integral from minus L to L of bm sine of m pi over L x times cosine of n pi over L x dx. Sorry, that should have been an n. Right, multiplying those. But we had this additional orthogonality property for the for combining sine and cosine terms, right? So this was this theorem over here. So this last integral is also 0, right? So this is also 0. And so therefore we end up with, this is equal to an times, well, if I integrate cosine of n pi over Lx squared, I get L, right? And so now if I divide by L on both sides, I get an is 1 over L times integral from minus L to L of phi of x cosine of n pi over Lx as claimed, right? Right, and so this is a particular example when n is not 0, how to calculate, like how to explain why this formula works for an. If that was, again, too long-winded, it's really just the orthogonality properties, right? You just plug in the Fourier series for phi. All of the terms are going to be 0 except one term, and that term will have an or bn, depending on if you plugged in a cosine or a sine term, and then you just normalize or divide by the constant, and then you get the formula, right? And so one good thing to remember is that sometimes it's hard to exactly remember what the formula is for these coefficients, like is it a 2 over L or a 1 over L, et cetera. All you have to remember are these orthogonality properties, and you can always rederive the formula very easily, right? Just doing this kind of sketch that I did over here. I know it looks like there's a lot of sums and integrals, so maybe if I say easily, maybe that's not going to be read in the best way, but it's easy in the sense that all the terms vanish except for one term, right? So there's not really much going on here once you know that there's the orthogonality, because everything is basically 0 except for one term. And so that's the sense in which it's easy. Okay. All right, and so what we're going to do to end the lecture today, and also we'll do we'll continue this at the start of the next lecture, is start calculating some examples. Right, so let's look at several examples of how to actually calculate these things. I mean, at the end of the day, all this is really going to end up being is just some possibly painful review of various integrals involving trig functions, right? So this is really what these problems reduce to if you want to actually calculate these coefficients. Right, but before we go into these examples, I just want to finally introduce one last definition, and then we'll turn to the examples. Sorry about that. Okay, so in order to motivate this definition, let's just go back to this theorem briefly. And so notice here, we're assuming in this theorem that the function phi that we're given has a Fourier series, in the sense that I know that phi of x is equal to this infinite sum of sine and cosine terms, right? Plus some a0 term. And assuming that phi had this form, we derived the formulas for what an and bn have to be using the orthogonality properties. So these things are usually called the Fourier coefficients, as I said before. Well, let's suppose we don't know that phi has a Fourier series. So let's say we don't know if phi is equal to this infinite sum, right? Well, you can still calculate these coefficients, right? As long as phi is like a, for example, a bounded function, these integrals will always be finite, right? And so you can still define the Fourier coefficients even if your function phi doesn't have a Fourier series. And so that's what this definition will be, right? So suppose phi of x is any function on, say, the interval between minus L to L. Or there's an analogous version for 0 to L, which you can infer from this. So I'm going to write this definition for the interval from minus L to L. For the formulas I'm about to write, just replace minus L by 0, and then they hold. Right. So the Fourier coefficients of phi are just an and bn as before. Right, so the same formulas. Right, so again, the key distinction is we're just given a function on the interval between minus L to L, or possibly between 0 and L, where L is just some fixed number that's being given to you. Maybe L is equal to pi. And we just have some function on this interval, which may or may not satisfy certain boundary conditions, and may or may not be equal to the Fourier series that we've been looking at before. You can still define the Fourier coefficients. And so the definition of the Fourier coefficients is take your function phi and just use these formulas. And these are the Fourier coefficients. And so going forward, the question for us will be, or one of the big questions for us will be, let's suppose we're given a function and we don't know it's equal to a Fourier series. Well, I can still calculate the Fourier coefficients, an and bn, and I can still write down this infinite series up here. And so the question will be, well, one, does this infinite series converge, which is a hard question in general? And two, is my function phi of x equal to the series on the domain, right? And that's also a hard question in general, so it's going to take several weeks to answer. Right. And so typically when you hear people talking about Fourier coefficients, they just mean for an arbitrary function on the domain, you can always calculate these coefficients. And this is separate from the claim that the function is equal to a Fourier series, right? So these are two distinct things. So for any function, you can calculate Fourier coefficients in theory, but not every function will be equal to a Fourier series is the distinction. Okay. Okay, well, with that definition in hand, let's turn to some examples. So I'll do one example to finish the lecture today, and then we'll do a few more at the beginning of the next lecture. So let's suppose for the first example, say my function phi of x is equal to 1 on the interval, say on 0 to L. Let's say the open interval between 0 and L. And we want to find the Fourier coefficients. An and bn, right? And in fact, let's just do the sign, right? So we're only looking at the interval between 0 and L, so let's find the sign Fourier coefficients. We'll do an example with full Fourier coefficients next time, right? So it's just going to be, say, an. Right, well, by definition, we have an is equal to 2 over L times integral from 0 to L of my function phi of x times sine of n pi over L times x with respect to x. Well, if my function phi of x is just 1, this becomes 2 over L times integral from 0 to L of sine of n pi over L times x dx. well, this turns out to be an easy calculation. The examples we'll see next time are not so easy. So if now I just take this fundamental theorem of calculus and take the antiderivative, right? Antiderivative of sine is negative cosine, and I just have to take into account the chain rule when I do this. So I end up with 2 over L times negative cosine of n pi over Lx times L over n pi, right? Because I'm reversing the chain rule. And I'm looking at this between x equals 0 and x equals L, right? Right, and so this ends up being, well, let me pull out the negative sign. So negative 2 over L, and then I have, well, let me actually pull out the negative sign and negative ln over pi. So I have negative 2 over L times L over n pi, and then I have cosine n pi over L times L minus cosine of n pi over L times 0. Again, we're just using the fundamental theorem of calculus. And so this ends up being negative 2 over n pi. And in parentheses, I have cosine of n pi minus cosine of 0, which is 1. Right? And so if you remember, well, notice that, okay, if you look at cosine of n pi, this is not, well, if n is equal to 1, or sorry, if n is equal to 0, it's equal to 1, right? But it's also true that if n is equal to 2, cosine of 2 pi is 0, and cosine of 4 pi is 0, and cosine of 6 pi is 0, and et cetera. So this is 1 if n is even. What happens if n is odd? Well, remember, what does the graph of cosine look like? So this is 0. Cosine is 0 at pi over 2, right? And so at pi, it's equal to negative 1, right? And then it goes up. And so it turns out that for every odd multiple of pi, cosine is negative 1, right? So if n is odd, right? And so what does this mean? Well, this means that if n is even, this is going to be 0, right? Because I'm going to have 1 minus 1. On the other hand, if n is odd, I get minus 1 minus 1. So I get negative 2 over n pi times minus 1 minus 1, which is, well, minus 1 is negative 2. Negative 2 times negative 2 is 4, right? So I get 4 over n pi. And so therefore, my coefficient an, well, it's equal to 4 over n pi if n is odd. And it's equal to 0 if n is even. Right, so for this particular function, the Fourier coefficient, the sine Fourier coefficients are 0 unless n is odd. Right, and so that's the answer, right? These are the sine Fourier coefficients for 1. On 0 to L. So one interesting point is that notice that it doesn't depend on L, which is not always going to be the case. I guess it's sort of expected because your function, the function phi is equal to 1 is the same everywhere, right? It doesn't really matter the L. But in general, again, the Fourier coefficients will definitely depend on L in some way. Right, and to end the lecture, I just want to finish with a question, which is related to the big question in the study of Fourier series. So we've calculated these coefficients, right? Right. So we've shown that if phi is equal to 1, the Fourier coefficients are an as above. And so the question is, does this mean that the function 1, this is my phi of x, is equal to the infinite sum from n equals 1 to infinity of an times sine of n pi over lx, right? Well, what does this mean? Let's plug in what we have. This would mean, right, and so this would be on on 0 to L. Right? This would mean that 1 is equal to, well, let me just write this as a list of, well, I only have terms corresponding to odd n. So I have 4 over pi, when n is equal to 1, I have sine of pi over Lx. Now, when n is equal to 2, it's 0, so I skip to n equals 3. So I have plus 4 over 3 pi sine of 3 pi over Lx. And then I have, well, the n equals 4 term is 0, so I go to n equals 5. So I have 4 over 5 pi sine of 5 pi over L x, and so on, right? I just keep going. It's an infinite sum. And so if we can solve this problem of like understanding when, let me rephrase that. So if for this particular function phi, I can write phi as a Fourier series on this interval, it would mean that this particular sum of different sines terms converges as if I like add up these terms in this way, they have to converge to 1, right? So this oscillating sum would equal 1 for every point x between 0 and L. Well, the thing to point out is that this is false if x is equal to 0 or x equals L, right? Right, because if, for example, if I plug in x equals 0, I just get 0 for every term. And if I plug in x equals L, I also get 0 for every term, right? So if I look at sine of n pi over L times x, this is always 0 if x equals 0 or x equals pi, or sorry, L. Well, if I'm adding infinitely many zeros, it still adds up to 0, right? And so I would have 1 equals 0, which is not possible. So this tells you it's not true if x equals 0 or x equals L. But this doesn't mean that it's false in between those points, right? It could still be true